Okay. Boom. I think we got it. So let's try that again. Hello, it's Sterling here. Technology is difficult, live streaming is hard, but we got it all figured out, I think. So, welcome to my first ever live stream. It's going to be a fun time dealing with the technical difficulties that will arise, but as you know, by clicking on the title, we're talking about neural networks today, and so I want to start learning really the math behind artificial intelligence, and so what better way to start than by doing 3 Blue 1 Brown's online course, if you will, of neural networks. So we're just going to start. Let me know if there's any problems, I guess, with the stream, but let's just get underway. So, of course, all the material in this is covered on his YouTube channel. He links some of the videos here, but we're just going through this interactive course, so let's get to it. So, the program above can identify hand-drawn digits 0 through 9 reasonably accurately. Give it a whirl if you haven't already. Alright? I like the number 7. Let's draw a 7. We'll see if the model's able to predict it as a 7. We got the neural network here, and let's see. Oh, 7. It went up. Hey, there you go. That's a great start. Should we try one more? Oh, sorry, I made it small. Let's try one more, because why not? If I can. Okay, I don't think I can. So let's just move on. Although it does generally work, it requires a bit of coaxing to get there. In particular, the digit images it receives need to be centered and about the right size, which is why there's a pre-processing step before the digit image gets passed along to the neural network. Right, yeah, we saw that in the model. Our focus will be on the network itself, but of course preparing data is important, sure. While more modern neural networks can do a much better job at tasks like this, the network above is simple enough that you can understand exactly what it's doing and how it was trained with almost no background. It's also simple enough that you could train it on your own computer, while training more sophisticated networks can require a truly mind-boggling amount of computation. Let's see what this is about. For example, when OpenAI trained their famous GPT-3 algorithm, it was estimated to require about $12 million worth of computation. I have not heard of that before, but definitely look into that, what exactly that algorithm is. Okay, so on the surface, a machine recognizing handwritten digits may not seem particularly impressive. After all, you know how to identify digits, and I bet you don't even find it very hard. For example, you can tell instantly that these are all images of the digit 3. Yeah, those look like 3s to me. Each 3 is drawn differently, so the particular light-sensitive cells in your eye that fire are different for each, but something in that crazy smart visual cortex of yours resolves all these as representing the same idea, while recognizing images of other numbers as their own distinct ideas. Right, so basically these obviously are all different images, but we can understand as humans that they're all 3s, and that's difficult for a computer to do, is the idea. But if I told you to sit down and write a program like the one shown above that takes in a grid of 28 by 28 pixels and outputs a single number between 0 and 9, the task goes from comically trivial to dauntingly difficult. Yeah, I mean, spoiler alert, this is a course about neural networks, but if I were just to think about how I would just program something like in Java or Python just alone, that's probably impossible, really. Or if not, virtually impossible. So, I think we're going to get on and learn about some neural networks. Somehow identifying digits is incredibly easy for your brain to do, but almost impossible to describe how to do. The traditional methods of computer programming with if statements and for loops and classes and objects and functions just don't seem suitable to tackle this problem. Yeah, so I can't teach you how to identify the number 3 or any number for that matter. That is something that makes programming it so difficult, because it would just be me trying to explain to the computer, but I can't even do that to a human. So that's not going to work. We need a better way. But what if we could write a program that mimics the structure of your brain? That's the idea behind neural networks. The hope is that by writing brain-inspired software, we might be able to create programs that tackle the kinds of fuzzy and difficult to reason about problems that your mind is so good at solving. Although they're inspired by the brain, they're not identical. Right, yeah. Moreover, just as you... Oh, we're almost at the first real part. Exciting. Moreover, just as you learn by seeing many examples, the learning part of machine learning comes from the fact that we never give the program any specific instructions for how to identify digits. Instead, we'll show it many examples of hand-drawn digits with labels for what they should be, and leave it up to the computer to adapt the network based on each new example. By the way, recognizing handwritten digits is a classic example for introducing this topic, and I'm happy to stick with the status quo here. Since it's such a common starting point, there are plenty of other resources available that tackle the same subject, more in depth for people who want to dig deeper. If that sounds like you, here's an online textbook which includes code. Perfect. Before we continue, I just want to make sure everything's running smoothly here. We're okay. Let's keep on going for now. The structure of a neural network. Wait, was it good? Because it's frozen. Okay, so the screen is frozen. Perfect. Okay, that's gonna be fun. Well, let's keep going. I hope you're doing all right. Just let me know if you're having any difficulty with the stream. I could see what I could do to fix it. So let's get into the structure of a neural network. This lesson is all about motivating and understanding the structure and mathematical description of a neural network, while the next lesson will focus on how to train it with labeled examples. There are many variants of neural networks, such as convolutional neural networks, recurrent neural networks, transformers, and countless others. In recent years, there's been a boom in research of these variants, but the first step to understanding any of them is to build up the simplest, plain vanilla form with no added frills. There it is, ladies and gentlemen, plain vanilla, aka multi-layer perceptron. It looks like this is going to identify digits. Yeah, and with a few layers of neurons. And it looks like this one did a good job because it's outputting 4, which, you know, as a human like me would say, that drawing is indeed a 4. So good job, 3 blue, 1 brown. Let's learn how he did it. Neurons. Right now, when I say neuron, all I want you to think is a thing that holds a number. Specifically, a number between 0 and 1. Neural networks are really just a bunch of neurons connected together. The number inside the neuron is called the activation of that neuron. And the image you might have in your mind is that each neuron is lit up when its activation is a higher number. So here, as you can see, the higher activations have a higher brightness, lower ones have a lower, and that's just a good way for humans to visualize it. So perfect. All the information passing through our neural network is stored in these neurons. So we need to represent the inputs and outputs of our image, the images and digit predictions, in terms of these neuron values between 0 and 1. Right. Right, yeah, so we need to make sure the input, the picture we give it, is just really a bunch of numbers between 0 and 1, and our output should be numbers between 0 and 1. That makes sense. All of our digit images have 28 times 28 equals 784 pixels, each with a brightness value between 0, black, and 1, white. To represent this in the network, we'll create a layer of 784 neurons, where each neuron corresponds to a particular pixel. So we have an animation here. Let's take a look at that. So they got the number 9. It's being stretched out. Okay, I see what they're doing. So they're taking the number 9 and breaking down each little pixel into 0 and 1 values based on the brightness at that pixel. And then they're taking each row of the picture and lining them up together. And you create this massive, massive row. And that's going to be the first left-handmost layer on the neural network. So, perfect. Let's keep moving. Let me check on the stream quickly. Looks like it's doing okay, right? Oh, YouTube's telling me there's an error. Let me check this out quickly. As we got, YouTube is not receiving enough video to maintain a smooth streaming. Okay, that is not... Videos or viewers will experience buffering. So I hope you don't have buffering. I hope you're enjoying the stream so far. Let's keep going for now. Right? Yeah. 3, 2, 1. Let's do it. Let's do it. Let's keep on going. When we want to feed the network an image, we'll set each input neuron's activation to the brightness of its corresponding pixel. Right, that's what we saw before. Right, we're only seeing the first and last neurons because way too many. The last layer of our network will have 10 neurons, each representing one of the possible digits. The activation in these neurons against some number between 0 and 1 will represent how much the system thinks an image corresponds to a given digit. Right, so what we saw from the first example in this lesson was when we drew a 7, at the end of the neural network, the 7 neuron lit up, and that was its prediction. So take a look at the following image. Based on the output layer of the network shown above, what kind of digit does this network think it's looking at? How certain does it feel? Well, we see that it's somewhat 4, somewhat 9. So I think it's pretty confused, to be honest. I don't think it's confident in its prediction. So let's go ahead and type this. The neuron thinks it is looking at either a 4 or a 9 and is not very confident in its prediction. The moment of truth. It's having trouble deciding whether the input image is a 4 or 9. Perfect! That is fantastic news. Alright, so let's move on. The hidden layers. There will also be some layers in between called hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits will be handled. In this network, I have 2 hidden layers, each with 16 neurons, which is admittedly kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment, and 16 was simply a nice number to fit on the screen. Well, that's convenient. In practice, there's a lot of room to experiment with the specific structure. Interesting. I wonder how we can decide how many layers is the correct amount. So now he's going to motivate, why should we use layers? You'll notice how in these drawings, each neuron from one layer is connected to each neuron of the next with a little line. This is meant to indicate how the activation of each neuron in one layer, the little number inside it, has some influence on the activation of each neuron in the next layer. Right, so we have an animation. The 7 is being broken down, right? And then it's feeding through the network. Each layer has influence on the next. He says, watching the activations in each layer propagate through to determine the activations in the next can be quite mesmerizing. However, not all these connections are equal. Well, since some will be stronger than others, And as you'll see shortly, determining how strong these connections are is really the heart of how a neural network operates as an information processing mechanism. But before jumping into the math or how one layer influences the next, or how training works, let's talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What's the best hope for what those middle layers are doing? Why not just directly connect all the pixels to the final output we want? Well, when you or I recognize digits, we piece together various components like loops and lines. So we got a 9 is just really a circle-ish thing with a long line. An 8 is 2 circles, and a 4 is 1 long line, 1 short line, and 1 horizontal line. I guess, yeah, that does make sense. So, in a perfect world, we might hope that each neuron in the second to last layer corresponds to one of these subcomponents. That any time you feed in an image with, say, a loop up top, there's some specific neuron whose activation will be close to 1. So, wait, one more time. In a perfect world, we might hope that each neuron in the second to last layer corresponds to one of these subcomponents. Right, I got it. So, ideally what we want is the last layer of our network to be able to determine, if we have a loop, then, it's probably a 9 or an 8, but it's not a 4. So, that's great. Let me quickly check, see how we're doing in terms of stream. Looks like we're doing okay. I see a little bit of buffering. That is not good. There we go. I think we're doing better now. So, let's move on. And I don't mean just this exact loop of pixels. The hope would be that any generally loopy pattern toward the top of the image sets off this neuron. That way, going from the third layer to the last one would only require learning which combinations of subcomponents correspond to which digits. Yeah, so we don't want to create something that will only memorize one specific 9. We want to make sure it understands anybody's drawing of 9. Because like in the beginning of the stream when I drew a 7, my 7 is definitely different than everyone else's. Well, everyone's just going to be pretty similar, but in terms of the exact pixels, right? That's what I'm getting at. Of course, this just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponent should be? And I still haven't talked about how exactly one layer influences the next, but run with me on this for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do that would be to first recognize the various edges that make it up. So, right, this loop is broken up into just small little lines. Similarly, a long line, as you might see in a 147, is really just a long edge. Or maybe you can think of it as a certain pattern of several smaller edges. So this long line can be broken down into a pattern of a couple smaller ones, right? That makes sense. So our hope might be that each neuron in the second layer of the network corresponds to some little edge. Maybe when an image comes in, it lights up neurons associated with all the specific little edges inside that image. This in turn would light up the neurons in the third layer associated with larger scale patterns like loops and long lines, which would then cause some neuron from the final layer to fire, which corresponds to the appropriate digit. Does the network actually do this? So in pixels, this is what our input is. The edges ideally look like this, and when we break it down into edges, the shapes, we got the loop and we got the line, and then ultimately it should predict the digit 9 in the end. Whether or not this is how our final network actually works is another question, one that we'll revisit after seeing how to train this network. But this is a hope that we might have. Alright, this is pretty neat. Let's make sure everything's running smoothly. I actually think it's running all right. So, looks like we have a little bit of buffering, but there we go. It should be good now. So, layers break problems into bite-sized pieces. You can imagine how being able to detect edges and patterns would also be useful for other image recognition tasks. Edge detection isn't just for digits. For all kinds of problems, like the line. Oh, that's pretty fascinating, actually. That's how AI can predict this image is one of a line with the edges. And beyond image recognition, there are all sorts of intelligent tasks that you can break down into layers of abstraction. Parsing speech, for example, involves parsing raw audio into distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. So, for example, if you're given audio, it can create the sounds. It might be able to have the R, E, all the letters. It'll combine groups of letters and ultimately combine into one large word of recognition. So that's natural language processing, I believe. I never really understood the technical side of how that works, so that's really interesting to know. That's definitely one side of AI I might be interested in exploring, is natural language processing. The layered structure of the neural network is great because it allows you to break down difficult problems into bite-sized steps so that moving from one layer to the next is relatively straightforward. Great. Let me check really quick. Yeah. I think the buffering is okay. It's doing alright. Let's keep it going. Right. We're doing okay? We're doing okay. We're doing okay. How information passes between layers. With this as a general idea, how do you actually implement it? That's what we're interested in, so let's get to it. I'm excited. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. It would be especially elegant if all of those different steps use the same mathematical procedure. That would be elegant, yes. Remember when we had the 9 that got converted into the little subparts, and then the bigger subparts, and then the 9 ultimately? It would be really convenient if we could do the same thing over and over to get our answer. So I expect to be heartbroken, but let's see, maybe we'll get lucky. To zoom in on one very specific example, let's say that the hope is for this one particular neuron in the second layer to pick up on whether or not the image has an edge in this spot here. So they've highlighted the spot with the white squares. We want this one specific, right, yeah. So I want you to think about what parameters the network should have, what knobs and dials you should be able to tweak so that it's expressive enough to potentially capture this pattern, or other pixel patterns, or the pattern that several edges can make a loop, and such other things, and other such things. What we'll do is assign a weight to each of the connections between our neurons and the neurons from the first layer. These weights are just numbers. So if you remember in the network, they had the lines that connected the layers together. Those are going to be the weight. And they are going to explain, or he is going to explain, what those weights actually are right now. Each weight is an indication of how its neuron in the first layer is correlated with this new neuron in the second layer. If the neuron in the first layer is on, then a positive weight suggests that the neuron in the second layer should also be on. And a negative weight suggests that the neuron in the second layer should be off. Okay, so for example, in this image, if we had let's take the first neuron, that has a blue weight. So that means it has a positive weight. And so what that means is if that neuron is on, it has a high value, that means that the neuron that's connected with it should also be on and have that high value. That's what I think he's getting at here. Of course, these weights will interact and conflict in interesting ways, but the hope is that if we add up all the desires from all the weights, the end result will be a neuron that does a reasonably good job of detecting the edge we're looking for, as long as the weights are well chosen. So to actually compute the value of this second layer neuron, you take all the activations from the neurons in the first layer and compute their weighted sum. So I wanted to understand the math behind neural networks. Here is our first, not equation, but expression, I guess. So W sub 1 times A sub 1 plus blah 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 all the way through W sub n, A sub n. So this is their weighted sum. This is very similar to taking the dot product of two vectors. I wonder if that is where this comes from. We'll see, but that is the weighted sum. It's helpful to think of all those weights as being organized into a grid of their own. So all these weights are in this grid right here that I'm hovering just below. And what this is if you remember from the beginning, they had the square of, I forget what number this is. Let's just say it's 9, I guess. They had the grid of 9, and each pixel was either black, somewhat white, all the way through perfectly white. And so now we're taking that idea and we're doing the weights, the same exact thing but with the weights. So take the very first neuron, right here, the one I'm pointing right over. So this one is somewhat on. It's pretty dark, but it is somewhat on. So because it has a positive weight, that means the second neuron that it's connected to should also be somewhat on. So if we take this very tiny first pixel in the top left corner, notice how the color is blue. And that's because it has a positive weight. And he made blue positive, red negative. For the next neuron in the first layer, it's also somewhat on. Its weight is blue, so the next tiny pixel to the right is blue. We get to the next red neuron after a couple more blues, or excuse me, the first red weight. We have a black neuron, which means that the second neuron it's connected to should do the opposite. And so you see at the top left we have a couple blue ones, but then we get our first red one. And that's similar, or that's exactly what's happening here in the network in the first layer. Let's just see if we're buffering. I don't think we are. I think we're doing all right here. Let's keep going. Each weight is associated with one of the 784 input pixels. Arranging the weights into this 28 by 28 grid makes the correlation between the input image and the output activation clear. I'm using blue pixels to indicate a positive weight, red to indicate negative, with the brightness of that pixel being some depiction of the weight's value. Oh, interesting. That is something I didn't pick up on. Oh, that makes sense. That makes sense. For example, take the fourth neuron. That is the brightest neuron we have in this depiction. Notice how its weight is much brighter blue than the ones above it. Well, that's because that neuron is much brighter than the ones above it. So that means when we are trying to recognize the number, or when we are trying to predict what the neuron connected to it is, we should predict that it has a very strong correlation to the previous neuron. So we expect a very bright white. And in fact, this is the first, second, third, fourth weight, it looks like. We have 1.87, or excuse me, maybe I'm looking at the wrong one. Sorry, with the brightness of that pixel being some depiction of the weight's value. Okay, well the thing is, it's not, actually I noticed that weight, the bright one is going to the third. But the third one is not that bright, so I'm not quite sure why it has a higher weight than the one below it, because the one below it is much brighter. If we take a look here, let's check weight 5. Right, that's the red one, so of course we expect it to be negative. I'm going to skip over that for now. Maybe it'll later on, hopefully immediately, but we'll see. What if we made the weights associated with almost all the pixels 0, except for some positive weights associated with these pixels in the region where we want to detect an edge? So what if we made all the weights 0 except for some positive weights with the pixels where we want to detect an edge. With these weights, the neuron in the second layer will be more activated when pixels in this region are more activated. So the neurons in the second layer will be more activated when pixels in this region are more activated. Sure. Then taking a weighted sum of all pixel values really just amounts to adding up the values of the pixels in the region we care about. A weighted sum, right, because all of the weights are going to be 0, so those terms in this weighted sum, here it is, all the terms that have a weight of 0 will just drop out, right? Oh, we have a question coming up. But this pattern of weights will pick up on big blobs of activated pixels, not just edges. To really pick up on whether or not this is an edge, you might want to have some negative weights associated with the surrounding pixels. Then the sum will be largest when these pixels are bright, but the surrounding pixels are dark. Okay, so the darker the neuron, if I'm correct, the darker the neuron, the more negative the weight. The brighter the neuron, the more positive. And let's see if that's true. Well, that's that same problem I was running into before. So I'm not quite sure. I think I get the general idea though. By adding some negative weights above and below, we make sure the neuron is most activated when a narrow edge of pixels is turned on but the surrounding are dark. So, suppose a neuron in the second layer has weights as indicated above. Rank the 4 images based on how they would activate that neuron, or by how much they would activate that neuron. Okay, so let's begin with A. If we had all black, we said the darker the neurons, the more negative the weight. That means that because it is very negative all across the board, it would pick up on the red and the other red, but not the two blues in between. So we'll say like that's half about. With B, I think that's pretty ideal. The white ones would get the blue ones lit up, and the red ones would be correct. So I think B has the best one, but let's keep going. C looks like the exact opposite. I think that one's the worst, because the black should be where the white is. The white should be where the black is. So nothing would be picked up. So far I'm saying B is greater than A, which is greater than C. So I'm leaning towards answer 2, but let's see. D, everything is white. It should pick up on the two blues. So I'm going to say B is greater than D, is greater than A, is greater than C. Let's check our answer. Ooh, we got it. Let's go. B gives the highest activation because it only activates the neurons with positive weights. C gives the lowest because it's the inverse, right? A has a weighted sum of 0 because all the input neurons are off, but D has a positive activation because it activates 24 positive weights, but only 16 negative weights. So, A has a weighted sum of 0. That's a thing I messed up on. A has a weighted sum of 0 because all the input neurons are off. And they said if they were all off, we give it a weight of 0. Correct. What if we made all the weights associated with it? Right. Okay, yes. If it's black, we gave it a 0. Nice. So, let's see how we're doing. Looks like we're still running pretty smoothly, minus some buffering. But for the most part, let's keep on going. So, hope you're doing alright. Hope you are enjoying the stream. Let's keep on grinding. So, sigmoid squishification. Ooh. The result of the weighted sum like this can be any number, but for this network, we want the activations to be values between 0 and 1. So it's common to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. So here's an animation. They took the number line and literally squished it into another number line's values between 0 and 1. There's no limit to how big or small the weighted sum might be, but our new neuron value should be between 0 and 1, so we need to somehow squish the range of possible outputs down to size. One common function that does this is called the sigmoid function, also known as a logistic curve, which we represent using the symbol. This one is the standard deviation one, sigma, I believe. That's why it's called the sigmoid function. Very negative inputs end up close to 0, very positive inputs end up close to 1, and it steadily increases around 0. So the activation of the neuron here will basically be a measure of how the weighted sum is. So if we get a very large weighted sum, it's going to be basically 1 will be the result of plugging it into the sigmoid function. As you can see here, as you move closer to the right, you get closer your y value to 1. Similarly, the smaller you get closer to 0. So the sigmoid function is just the squishing function we need. Perfect. So sigmoid of negative 1000 is closest to which of the following values? Well, we said that if we look at this graph, negative 1000 is all the way to the left. So that means it's going to be very close to approaching 0, right? And we can even do the math here. They define the sigmoid function as 1 over 1 plus e to the minus x. So if we plug in negative 1000 there, we get 1 over 1 plus e to the 1000, because negative times negative 1000 is positive 1000. So you get 1 over 1 plus e to the 1000. We can take e to the 1000 to be some huge number. Let's just call it a huge number. If we add 1 to it, it's not going to change much. 1 over a huge number is about 0. So that's another way of proving that our answer should be 0. So let's check it. That's correct. Nice. We're making good progress here. So, but maybe it's not that we want the neuron to light up when this weighted sum is bigger than 0. Maybe we only want it to be meaningfully active when the sum is bigger than, say, 10. That is, we want some bias for it to be inactive. Okay, what we'll do then is add some number like negative 10 to the weighted sum before plugging it into the sigmoid function that squishes everything into the range between 0 and 1. We call this additional number a bias. Right, didn't they just say that? So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how big that weighted sum needs to be before the neuron gets meaningfully active. So the weighted sum must be at least 10 here to create a neuron that's meaningfully active. More neurons. And that's just one neuron. Every other neuron in the second layer is also going to have weighted connections to all 784 neurons from the first layer. Each neuron also has some bias, some other number to just add on to the weighted sum before squishing it with the sigmoid. That's a lot to think about. With this hidden layer of 16 neurons, that's 784 times 16 weights and 16 biases. And all of this is just the connection from the first layer to the second. The connections between the other layers also have a bunch of weights and biases as well. All said and done, this network has 13,002 total weights and biases. 13,002 knobs and dials that can be tweaked to make this network behave in different ways. And that's how they calculated 13,002. When we talk about learning, which we'll do in the next lesson, we mean getting the computer to find an optimal setting for all these many, many numbers that will solve the problem at hand. One thought experiment, which is once both fun and horrifying, is to imagine setting all these weights and biases by hand. Purposefully setting weights to make the second layer pick up on edges, the third to pick up on patterns, and so on. I personally find this satisfying rather than just treating these networks as a total black box. Because when the network doesn't perform the way you anticipate, if you've built up a feel for the meaning of those weights and biases in your mind, you have a starting place for experimenting with how to change the structure to be better. And that's exactly what I'm trying to do here, is I understand. I took a course over the summer on artificial intelligence, and we learned a bunch in Python and whatnot, but we never really understood what was happening with our neural networks. It just happened. So what I'm trying to do is really understand, when something goes wrong, what can we do to fix that? Why is this happening? And I think this is the right starting point for me, because he said the next thing we're going to do is talk about some of the learning, machine learning. So, perfect. I'm excited. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. So more compact notation. Let's just make sure we're doing alright and not lagging, because that would suck. Yeah, I think we're doing good. It might be buffering. Hope you are doing well. Let's continue. More compact notation. The actual function to get one's neurons activation in terms of the activations in the previous layer is a bit cumbersome to write down. So we have the sigmoid function, and as input we are taking the weighted sum, and this is only for one neuron, so imagine doing this for all the neurons. Tracking all the indices takes a lot of effort, so let me show the more notationally compact way that these connections are represented. Instead of computing a bunch of weighted sums like this one by one, we'll use matrix multiplication to compute the activations of all the neurons in the next layer simultaneously. So yeah, like I said, this is basically just taking the dot product of two vectors, because that's how matrix multiplication is going to work. First, organize all the activations from the first layer into a column vector. Let's see what that looks like. So they took all the activations from the first layer, made it one vector. Now organize all the weights as a matrix, where each row of the matrix corresponds to all the connections between neurons in the first layer and a particular neuron in the next layer. See what that looks like? Okay, they put it before, and these are all those weights. Okay, and then they're going to continue that for the second neuron in the second layer, and then the third. Those will all be the different rows of the matrix. Then the product, WA, is for the 0th neuron, is a column vector containing all the weighted sums for the neurons in the next layer. So let's see. It means our result so you got some answer, right. Instead of talking about adding the bias to each one of these independently, we present it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. I guess that's a convenient way of doing it. Right. Because when you do this, that's going to add them individually to each one, so no worries there. Finally, I'll wrap a sigmoid on the outside here, which is meant to represent applying the sigmoid function to each component of the result. And so they just do that. Perfect. So once you write this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in a neat little expression. Ooh. That is cool. That is cool. So let's try to understand this a little bit. So the first neuron is equal to, you take the sigmoid function, input it, the weight times the activation of the 0th plus the bias. And when I say the first neuron, I mean the first layer. So if we call our first layer the 0th one, the one all the way on the left to be the 0th, the next layer is going to be the first. So the activation of the neuron in the first layer is equal to the sigmoid function of the weight times the activation of the neuron in the 0th layer plus. This makes the relevant code much cleaner and faster, since many libraries optimize the heck out of matrix multiplication. Nice. We're almost done here with this first lesson. The network is just a function. Earlier, I said to think of these neurons simply as things that hold numbers. Of course, the specific number these neurons hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function. It takes in the activations of all neurons in the previous layer and spits out a number between 0 and 1. And really, the entire network is just a function. It takes 784 numbers as its input and spits out 10 numbers as its output. It's an absurdly complicated function because it takes over 13,000 parameters, weights and biases, and it involves iterating many matrix vector products and sigmoid squishifications together. But it's just a function nonetheless. Right. So we are finished with this first lesson. Next up, learning. In a way, it's kind of reassuring that this looks complicated. If it were any simpler, what hope would we have in taking on the challenging task of recognizing digits? True. And how does it take on that challenge? How does the network learn the appropriate weights and biases from data? That's what I'll show in the next lesson. One asterisk about the sigmoid. Blah, 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 blah. Problems with the sigmoid function. I think just to save time, we can continue on. This is the ReLU function. They're saying that's a good replacement, but for now, we'll stick with sigmoids because we're introductory, and that's what 3 blue, 1 brown wants. So, that being said, we finished the first lesson. So, let's go ahead and move on to the second one. I think I'm going to stop there after we finish the second lesson, but I'm excited. Let's get into what I'm excited about. We learned a little bit about the math already. We are now going to actually understand how the network learns, which will involve more math, as we discuss gradient descent, how neural networks learn. So just to make sure we are doing good, I think. I think we're doing fine with this stream. Yeah. I think we're fine. So, let's do it. Gradient descent. How neural networks learn. In the last lesson, we explored the structure of a neural network. Now let's talk about how the network learns by seeing many labeled training data. The core idea is a method known as gradient descent, which underlies not only how neural networks learn, but a lot of other machine learning as well. Cool. So here's a quick recap. We wanted to recognize handwritten digits, the hello world of neural networks. Yeah, because when you learn to program for the first time, your first assignments are system.out.println, hello world for Java, hello world for Python. Right. These digits are rendered onto the grid, right? Each pixel has some value between 0 and 1 and black through white. 784 values determine the activations of the neurons in the input layer. The activation for each neuron is based on a weighted sum of all activations from the previous layer plus some number called the bias. We then wrap a nonlinear function around the sum such as a sigmoid or a ReLU. And we did a sigmoid. In this way, values propagate from one layer to the next, entirely determined by weights and biases. The brightest of the 10 neurons in the output layer is the network's choice for which digit the image represents. So, see, there's a 4 is the choice, or, excuse me, they're doing a 7 now. Let's see. Yep, they got the 7. Perfect. And that's the one that lit up. In total, given the somewhat arbitrary choice of 2 hidden layers with 16 neurons each, this has 13,002 weights that we can adjust, and biases that we can adjust. These are the values that determine what the network does. Remember, the motivation was that maybe the second layer could pick up on edges, the third wake loops and lines, and the last one pieces them together to recognize digits. Perfect. So let's get into it. How does the network actually learn? Well, let's find out. What makes machine learning different from other computer science is that you don't explicitly write instructions for doing a particular task. In this case, you never actually write an algorithm for recognizing digits. Instead, you write an algorithm that can take in a bunch of example images of handwritten digits along with labels for what they are and adjust those 13,002 weights and biases of the network to make it perform better on those examples. The labeled images we feed in are collectively known as the training data. So here we have all the images and then they're labeled with what they represent. So the first one is a drawing of a 0, and then we tell it, there's a 0. That's what that image is of. It's of the number 0. Hopefully the layered structure will mean that what it learns generalizes to images beyond the training data. To test this after training the network, we can show it more labeled data that it's never seen before and see how accurately it classifies them. So that's like, I don't know, if you're taking a math class, you don't memorize your homework because then you're going to fail the test if you don't know how to do the concepts, right? So what we're trying to do is prevent the network from memorizing the pictures, because once it gets real world data per se, it's going to have no idea what to do if it's only memorized the training data. So we want to teach it. We want the machine to learn. This process requires a lot of data. Fortunately, the good people behind the MNIST database have put together a collection of tens and thousands of handwritten digits, each labeled with the number they're supposed to be, that we can use for free. Perfect. I should point out that although it can be provocative to describe a machine as learning, once you see how it works, it feels a lot less like some crazy sci-fi premise and a lot more like a calculus exercise. It really just comes down to finding the minimum of a specific function. So the cost function. Remember, our network's behavior is determined by all of its weights and biases. The weights represent the strength of connections between each neuron in one layer and each neuron in the next. And each bias is an indication of whether its neuron tends to be active or inactive. To start things off, initialize all the weights and biases to be random numbers. This network will perform horribly on the given training example since it's just doing something random. For example, if you feed in the image of a 3, the output layer looks like a mess. There's a bunch of highlighted results, and he boxed them and said, utter trash. Because it is. We don't get an answer. We just get a bunch of nonsense. So how do you programmatically, interesting. So how do you programmatically identify that the computer is doing a lousy job and then help it improve? What you do is define a cost function, which is a way of telling the computer, no, bad computer. That output layer should have activations which are 0 for most neurons, but with a 1 for the third neuron. What you gave me is utter trash. What's the cost of this difference? So, we measure how badly the network is doing by comparing its results to the correct answer. To say that a little more mathematically, add up the scores of the differences between each of these trash output activations and the values you want them to have. We'll call this the cost of a single training example. The cost is small when the network confidently classifies this image correctly, but large when it doesn't know what it's doing. Exercise. Suppose the network is shown an image of a 4. Rank the costs associated with each of the possible outputs shown above. So, we said we wanted to add up the scores of the differences between each of the trash output activations and the values you want them to have. Okay, sure. So ideally, we want it to have a 1 for just the 4. So we're given a 0 for all of them. So each of the terms are going to be 0 squared, except for the 4. It's going to be 0 minus 1 squared, which is 1. So for A, we have 1. B is perfect. We're going to get 0, because 0 minus 0 for all the terms is 0. 0 squared is 0. And then for the 4, it's perfect. So 4 minus 4, 0 squared is 0. So the cost is worse in A than B. C, it will have the same amount, right? And it's going to be, let's just say, I don't know, if they said this amount, we could say like a half. So if we did a half minus 0 for all of them, that is 1/4 times 1, 2, 3, 4, 5, 6, 7, 8, 9. So a fourth times 9 is 9/4, and then 10/4 because 1 minus a half is a half squared. So 10/4, so that's more costly than A. So C is greater than A is greater than B because we got 10/4, 1, and 0. Or in order, 1, 0, 10/4. 10/4 is more costly than 1, which is more costly than B. And then with D, I think we did it the worst because everything is wrong. So we're going to get 1 squared for all of them. That's going to give us like 9. So it should be, in my professional opinion, D is greater than C, is greater than A, is greater than B. Let's check our answer. Yes. B has the lowest cost because it is the ideal output, and D has the highest cost because it is the worst possible output. A has relatively small cost because 9 of the 10 values are perfect, and only the output neuron corresponding to the digit 4 is wrong. C has a much higher cost than A because all of its output neurons are wrong, seemingly by quite a lot. Yeah, seemingly. So, I think we're doing okay with the stream. Just checking really quickly, we are doing well. Let's continue. Or maybe we're doing well. I don't know. You're watching it, not me. I hope it's working well. The cost over many examples. But we aren't just interested in how the network performs on a single image. To really measure its performance, we need to consider the average cost over all the tens of thousands of training examples. This average is our measure of how lousy the network is and how bad the computer should feel. That is, to put it lightly, a complicated function. Remember how the network itself is a function? It has 784 inputs, 10 outputs, and 13,002 parameters. Right, that is complicated. The cost function is a layer of complexity on top of that. The inputs of the cost function are those 13,002 weights and biases, and it spits out a single number describing how bad those weights and biases are. It's defined in terms of the network's behavior and all the tens of thousands of pieces of label and training data. In other words, this training data is a massive set of parameters to the cost function. Okay, so now we're going to do some calculus. Yay, minimizing the cost function. Just telling the computer what a terrible job it's doing isn't very helpful. You want to tell it how it should change those 13,002 weights and biases so as to improve. We can do better, growth mindset. Yes, I agree, we can do better, and let's have a growth mindset. To make it easier, rather than struggling to imagine this cost function with all these inputs, let's imagine a simple function with one number as an input and one number as output. So we got like a parabola here, it looks like. We'll imagine that the cost function has one input, right? How do we find an input that minimizes the cost? Well, we could take the derivative of the function and set it equal to 0, and then we could, make a sign chart to figure out what are the positive values, what are the negative values. For what x values is the function, is the slope, the derivative, positive or negative. But that's not what we're going to do, turns out. How do you find an input that minimizes the value of this cost function? Calculus students will know you can sometimes figure out that minimum explicitly by solving for when the slope is 0. Correct. And that's basically what the derivative is as a function of the slopes. And so we'll say that's not always feasible for really complicated functions. It certainly won't be for a 13,002 input function defined in terms of an ungodly number of parameters. So, for a complicated cost function, computing the exact minimum directly isn't going to work. So we'll have this crazy function, we're not going to take the derivative of it. A more flexible tactic is to start at a random input and figure out which direction to step to make the output lower. Specifically, find the slope of the function where you are. If the slope is negative, shift to the right. If the slope is positive, shift to the left. That's a good idea, actually. I hadn't thought of that. So by following the slope, we approach a local minimum. Let's see this in action. So we're starting at this random value. The slope is positive, so we're moving to the left. Now it's negative, so we move to the right. More negative, we move it to the right until we get to that minimum value. Clicking the new slope, or checking the new slope at each point, and doing this repeatedly, you approach some local minimum of the function. The image to have in mind is a ball rolling down a hill. Okay, so my eye caught attention of this ball on the left. So they all come together. Right, okay. Notice even for the simplified single input cost function, there are many possible valleys you might land in. It depends on which random input you start at, and there's no guarantee that the local minimum you land in will be the smallest possible value for the cost function. Also, notice how if you make your step sizes proportional to the slope itself, when the slope flattens out towards a minimum, your steps will get smaller and smaller, and that keeps you from overshooting. So as the slope gets shallower, take smaller steps to avoid overshooting the minimum. So we have some big slope, so we go down a lot, and then as the slope becomes more and more close to zero, as it gets closer to zero, a flat line, we're going to take smaller steps until we reach that zero value, and that's going to be our local minimum. So before we bump up the complexity, let's just make sure we're doing okay. Looks like we are. That is fantastic news. Hope you're enjoying the stream so far. So let's bump up the complexity a little bit. Imagine a function with two inputs and one output. You might think of the input space as the xy plane, with the cost function graphed as the surface above it. Okay, so we have this xy plane on the left, and then the cost function is on the right. This is the three-dimensional version. Of course, this isn't 13,002. It's only 3 dimensions, but we're getting closer. But we're just trying to visualize how this might look. Starting with a random value, look for the downhill direction and repeatedly move that way. So we're trying to get to, the minimum is going to be the bottom. So we're going to go down that shape until we get into the very bottom. Instead of asking about the slope of the function, you ask which direction you should step in this input space to decrease the output of the function most quickly. Again, think of a ball rolling down a hill. Beyond slope, using the gradient. In this higher dimensional space, it doesn't really make sense to talk about the slope as a single number. Instead, we need to use a vector to represent the direction of steepest ascent. Those of you familiar with multivariable calculus, not me, will know that this vector is called the gradient, and it tells you which direction you should step to increase the function most quickly. So I'm not going to let that stop me. We're going to figure this out. Figure it out mindset, right? Naturally enough, taking the negative of that vector gives you the direction to step which decreases the function most quickly. What's more, the length of that gradient vector is an indication for just how steep that steepest slope is. The gradient delta c, or it's an inverse delta, so I don't know what to call that, gives the uphill direction, so the negative of the gradient gives the downhill. So if we have a positive gradient, we're going uphill. If we have a negative gradient, we're going downhill. For those of you unfamiliar, check out some of the work I did on Khan Academy. But for now, all that matters is that, in principle, there exists a way to compute the vector, which tells you what the downhill direction is and how steep it is. You'll be okay even if you're not rock solid on the details. Perfect. We're just trying to understand this, right? So that's fine. We can dig into the multivariable calculus afterwards if need be. So the algorithm for minimizing this function is to compute this gradient direction, take a step downhill, and repeat that over and over. This process is called gradient descent. So we're going to compute the gradient, take a small step in the negative gradient direction, and then repeat. So gradient descent just means walking in the downhill direction to minimize the cost function. And remember, our cost function is specifically designed to measure how bad the network is at classifying the training examples. So changing the weights and biases to decrease the cost will make the network's performance better. Remember, this cost function involves an average over all, right? So minimizing it means a better performance on all the samples. In practice, each step will look like minus n times the gradient where the constant, well, that's not an n, I'm not sure what that variable is, but we'll call it n, because I'm such a noob at this, where the constant n is known as the learning rate. The larger it is, the bigger your steps, which means you might approach the minimum faster, but there's a risk of overshooting and oscillating a lot around that minimum. I'm sorry, I have to look this up to see what this is called. I've literally never seen this before. This is called eta, or eta. I think I'll call it eta. It's a Greek letter. Eta. Nice. What do you know? Let's just review that quickly. The larger that is, the bigger your steps, which means you might approach the minimum faster, but you might overshoot. Right. It's the same basic idea for a function with 13,002 inputs instead of 2. I'm still showing the picture of a function with 2 inputs because the nudges to 13,002 dimensional input are a little hard to wrap your mind around. Yes, we live in a 3D world, not a 13,003. But let me give you a non-spatial way to think about it. Ooh, okay. Did we have any animation? I don't think we did. I know in the videos there are, but cool. Another way to think about the gradient. Imagine organizing all the weights and biases for the entire network into one big column vector with 13,002 entries. Then the negative gradient of the cost function will also be a vector with 13,002 entries. The vector on the left is a list of all weights and biases. The vector on the right is the negative gradient, which is just a downhill, which is just a list of all the little nudges you should make to the weights and biases in order to move downhill. The negative gradient is a vector direction in this insanely huge input space that tells you what nudges to those 13,002 numbers would cause the most rapid decrease to the cost function. Each component of the negative gradient vector tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of the components in this gradient tells us which of those changes matters more. So, the negative gradient tells us what nudges would cause the most rapid decrease to the cost function. Each component of the negative gradient vector tells us two things. The sign tells us whether the corresponding component of the input should be up or down. So, if it is negative, we want to decrease the component in the input vector. Then the magnitude, the relative magnitudes, tells us which matters more. So if you have a greater magnitude, like 1.25 there, you're going to shift it a lot instead of a little bit. You see, in our network, an adjustment to one weight might have a greater impact on the cost function than an adjustment to some other weight. Consider the image below and suppose that the network is supposed to be classifying its input as a 3. So this yellow weight matters a lot. It's very bright. That's what we said earlier. The brighter the neuron, the more positive the weight. The brighter the weight, the more important. And then the black one, who even cares about this weight? Some of these connections just matter more for our training data than others. And a way you can think about the gradient of our massive cost function is that it encodes the relative importance of each weight and bias. That is, which changes will carry the most bang for your buck. So if the cost function is a layer of complexity on top of the original neural network function, its gradient is one more layer of complexity still, telling us what nudge to all these weights and biases causes the fastest change to the value of the cost function. The algorithm for computing the value of this gradient vector efficiently is called backpropagation, which we'll dig into in the next lesson. There, I want to take the time to really walk through what happens to each weight and bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant formulas. The main thing I want you to understand here, independent of implementation details, is that when we refer to network learning, we mean changing the weights and biases to minimize a cost function, which improves the network's performance on the training data. But before we continue on to learn the details of this gradient, let's take a brief sidestep to dig into what this network looks like after it's trained. So we just finished our second lesson here. And I said we were gonna only take a look at 2. Let's take a look at this third one. This is a really short one, and I feel like for when I post this replay, it's currently 8:52, about to be 8:53 p.m. So if we finish up at 9, we could definitely take a look at this third chapter here. It's really short. So analyzing our neural network. Before we do, let me just make sure again to see if everything is running smoothly. It looks like it is. That is great. Fantastic. Yeah. So let's just dig right in. Analyzing our neural network. In the last post, we learned about how training a neural network involves minimizing a cost function with gradient descent. In the next post, we'll dig into how the relevant gradient is computed. But before that, as a brief interlude, I want to skip ahead and have you look at what the result of the whole process is. This entire mini lesson will be about analyzing the trained neural network to see exactly what it does and why. But before you do any reading, it's good to get your hands messy and try to discover for yourself exactly what this network's up to. That's why we're bringing back the digit drawing demo from the very first lesson. Let's go. But this time, to aid in your experimentation, all the neurons update live as you're drawing, so you can get an immediate sense of how the input pixels affect the hidden layers and eventually the output. Ooh, that's a cool update. So immediately it's going to guess 7. Let's put 1 dot. Got a 5. Okay. Let's see. I think I'm going to draw a 4 actually. Let's see. Oh, it got that. Ooh, it went back to 5. This is intense. Oh, now it's at 4. Ooh, it says 2 now. I wonder why it says 2. What might be activating these specific neurons here? But let's see if we could get it. Oh, now it's saying 4 again. And at this point, oh, it just got much stronger. Yep, 4 is its answer. Let's just draw it in fully. Alright. And there you have it. 4 is the result. Good job. Spend a bit of time experimenting, yep, and then we'll discuss. Okay, so, analyzing the network. The network we developed with 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, is not bad. It classifies about 96% of new images it sees correctly. And honestly, if you look at some of the examples it messes up on, you feel compelled to cut it a little slack. So the first one, I would say has a 5, maybe. But it said 6. I could see that. The 9, 4, yeah. What is that one? Is that a 4? I guess 6? I don't know. I could see that. Yeah, this one's a bit rougher. I would personally say 7, but I get how it's a 4. Also, this one, I don't know what this is. A 1, maybe. It guessed a 3. This one kind of might be a 6. It guessed 0. Okay, if you play around with the hidden layer structure and make some tweaks, you can get this up to about 98%. Pretty good, although it's not the best. Wow. Modern neural networks, which add in more specific ideas than our plain vanilla variant, can have testing accuracy as high as 99.7%. And frankly, looking through the MNIST database, I'm not even sure if most humans could do better than that. Given how daunting the initial task is, there's something incredible about any network doing this well on images it's never seen, given that we never specifically told it what patterns to look for. Exactly, that's the beauty of this. We're not programming this, hard coding anything. If you see this, identified as a 4. No, we're just playing around with a bunch of numbers, and it is creating these accurate predictions. So what are the layers doing? Originally, I motivated this layer structure by describing a hope that the second layer might pick up on little edges while the third picks up on subcomponents that form a digit. So is this what our network has actually learned to do? Well, for this one at least, not at all. Interesting. Remember in the first lesson I said the weights leading to a given neuron in the second layer can be visualized as a pixel pattern that the second layer neuron is picking up on? The weights given to a given neuron in the second layer is a pixel pattern. Correct. When we look at the weights associated with the transition from the first to the next, instead of picking up on isolated little edges, they look almost random. There are some loose patterns, but hardly the ones we might expect. Exactly. It seems that in the unfathomably large 13,000 two-dimensional space of possible weights and biases, the network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on more generalizable patterns. To really drive this point home, watch what happens when you input a random image. Looks like a 5 to me. Yeah, I don't agree. And notice how, remember when we were playing with the model, when we just cleared the image, I think it recognized it as a 7 immediately, even though there was nothing there. So, if I gave you a blank piece of paper and said, what number did I draw? You would not say 7. So, this is just proving the point. If the system was intelligent, you might expect it to feel really uncertain, either not really activating any of those 10 output neurons or activating them all evenly. Instead, it confidently gives some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. This suggests that even if a network can recognize digits, it has no idea how to draw them. Much of this is because it's such a tightly constrained training setup. From the network's point of view, the entire universe consists of nothing but clearly defined, unmoving digits centered on a tiny grid, and its cost function never gave it an incentive to be anything but utterly confident in its decisions. You might wonder why I'd introduce this network with the motivation of picking up on edges and patterns when that's not at all what it ends up doing. Well, this is not meant to be an end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. You need to understand this before getting to the more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what's going on in these hidden layers, the less intelligent it seems. Let's return to the drawing demo. These second layer weight grids, which aren't really picking up on the edges we hope for, but instead on some strange blobby shapes, are visible within the demo if you click on any neuron in the second layer. So, okay. Here they all are. We see that for all of these, we can see exactly which are the positive weights, which are the negative ones, and their magnitudes, which are the strongest, which are the weakest. What's even cooler is that if you're looking at the weight grid for a particular neuron while drawing a digit, you can watch the weights be revealed, which changes the weight of the neuron. One fun challenge is to try drawing a 3 and then slowly extending it so it becomes an 8. At some point, the network's prediction will change, and as that's happening, watch for which neurons in the second layer are changing, and then to figure out why they change as the 3 becomes an 8. So we start with a 3, we have to clear it, and then slowly extending it so it becomes an 8. So let's see what's happening there. So we start with a 3. It guesses that, and then we're going to start making it an 8, and you see there, this neuron changed for sure. But now it gets more and more confident. You see a couple more of the neurons changing. That was a bad 8, wasn't it? Well, that's what you get when you start with a 3. So let's take this one right here. See what happens. It actually gets brighter and brighter until we draw the 8. As you spend time playing with the network, you'll start to find all kinds of edge cases where it gets confused or gives the wrong answer or just behaves in a way that isn't as intelligent as we might hope. The technology is cool, but it's not perfect. Again, think about what a constrained training environment this network had. Every digit that it saw was of a particular size, centered in frame. So if you give it something that's too big or too small or not quite in the center, it's bound to get confused. Last but not least, our current learning algorithm does nothing to let the network transfer knowledge of patterns does nothing to let the network transfer knowledge of patterns picked up on one region of the grid to another, or to make inferences about scaling. In fact, nothing about our training algorithm even uses the fact that some pixels are adjacent to others. If you start thinking hard about how to change the structure of this network to allow for more flexible learning, or how learning a pattern in one part of the image can naturally transfer to any other part, you'll be well situated to learn about some of the more modern variations on this theme, most notably convolutional neural networks. But we're getting ahead of ourselves. Before that, it's time to learn about backpropagation, the workhorse behind neural network training. So, we are now at chapter 4. This is where I think we're going to stop for today. Definitely, if we go into this, we see we have the backpropagation chapter and then the backpropagation calculus, the math behind it. So I think what my plan is going to do is to create a second stream to finish up on this mini course. And then after that, I might do more live streams. There's this free course on Udacity that I started last year. And maybe if you're interested, we could just go through it together and just explore, play with the code, work on some of the code live. I think that would be a fun idea. But for now, we got through the first 3 chapters. I'm very pleased about the progress. And now I have some pretty good understanding of how neural networks actually work. And I hope you do too. So thank you very much for studying with Sterling, and have a great rest of your day. Thanks for watching. Bye.